something like that, for this section. So you guys did very well, but I don't have those to hand back today. I will have them on Friday. So the office that they were being stored in wasn't open before 9, and that's when I started teaching. So I didn't get a chance to get up there and grab those. That was an oversight on my part, but I'll have those to hand back on Friday, and then I'll get kind of answer keys posted up on Canvas so you can kind of work through, see which ones you got wrong, and hopefully kind of improve kind of moving forward. You didn't do as well as you wanted, as you would have liked on that first exam. As we kind of take the next two, the weighting could change. So right now on Canvas, it currently shows your exam's weighted as 30%. So it shows it for everyone. So it's assuming that's going to be your best exam. But if you do better on the other ones, right, well, then that old exam gets bumped down to 20, and then your best exam will be 30. And then if you do better on both of the next two exams, this current exam would be bumped all the way down to only weighting 10% of your overall grade. So right now it's kind of like treating it as though it's your best exam because we haven't taken them all yet, right? But as we kind of progress through semester, that could change. Okay? I also have the second Excel assignments graded and moved everything down into their categories where they're being weighted according to the syllabus. So notice we've got our 2 Excels, 2 Connect homeworks, the online quizzes that we have, which I've got one for today as well. I'm in the wrong section. I just noticed because that due date is 10 o'clock for this section. Right, it'll be due before we start class on Friday at 11. Okay, so make sure you get that done before we start class. It should be pretty easy points. The questions that it has, if you get on and get this done, you'll see the questions are pretty easy after today's lecture, I think. Okay. Anything else I want to say there? Oh, just to full transparency, I gave everybody full credit for question 12. So the correct answer was typed in a little bit wrong. So like instead of 0.2243, it would have been like 0.2423. Like I typed 2 things, and it would have been close, but just in case it was someone that made them second guess, I wanted to make sure everyone was kind of given credit for that question. Okay. So overall, the average of the exam ended up I like to see it. I think we're in a pretty good place. I will say, like, I think I just look at the means across my different sections, attendance is highly correlated with performance. So I would just mention that moving forward, like the physical attendance, like in person. And I can see a lot of you, if you're not here or watching the kind of recorded lectures, but the sections that have higher attendance are also the ones that did better. Go figure, right? So that's kind of where we're at with that. Are there any questions related to that before we kind of jump into material for today? All right, so I posted an announcement as well right before class. I'm gonna have to cancel my office hours today, but I'll kind of take those 2 hours and I'll be available tomorrow from noon to 2 and then 3:30 to 4:30 as well, okay? So, we don't have any kind of outstanding assignments yet, and so I doubt I'll get too many of you kind of stopping by, but just in case you did, I wanted to mention that. Also, I put up that standard normal Z table under the files section on Canvas, so we'll take a look at that today, and we'll be using that a lot moving forward. Okay, so maybe printing that out, as I mentioned last class, might be something that's beneficial. So with that being said, I don't want to waste too much on this early stuff, so I'll probably go through this pretty quick. So last class, we talked about the uniform distribution. Right? It was a very specific type of continuous random variable. Today, we'll talk about the normal distribution, another specific type of a continuous random variable. Okay? So we'll kind of start out with the story of this guy. His name was Carl Gauss. He was, excellent at a bunch of different stuff, along with another mathematician, discovered this normal distribution. Okay. So sometimes we'll call this normal distribution the Gaussian distribution after him. Sometimes you'll hear it referenced as like the bell curve. But we see it pop up a lot. So story about him goes, he was an incredibly brilliant guy, even when he was young. Right, he was in school acting up, and the teacher told him, go over in the corner, count all the numbers up from 1 to 100. Thinks this is going to take him for a while, kind of calm him down. Comes back in a matter of seconds. So how could he do it so quickly? Right, 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5. It's going to take a while. Well, if we think about it, what does 1 and 100 add up to? 101. 2 plus 99 is 101. 3 plus 98, is 101. That continues all the way down to 50 plus 51, 101. So you basically have 50 pairs. They all add up to 101. 50 times 101 is what, 5,050, right? So even at a young age, he was able to kind of think in this mathematical way. In fact, there's an actual formula. If you want to add up from 1 to any number, you can actually just plug in what that n number is, and this equation would tell you what that sum would be. Now, we're not going to use this. This is kind of a cute little anecdote about this guy, but right, this would be the actual formula that you could use to do that. Okay. So he's, really smart guy, comes up with this normal distribution, and it's really interesting. It kind of pops up everywhere. So we see it like human height. If you were to like graph out the histogram or look at the distribution for human height, follows a normal distribution. If we look at rainfall, temperature, weight, a lot of other things tend to follow this normal distribution. Now, just because something's normally distributed doesn't mean they're all exactly the same, right? So normal distributions, right, we've got a whole bunch of different types, okay? So, even if you just think about like human height and temperature, right, they're even in different units, but they're still both normally distributed, okay? So he wrote all this in this book, right? And we ultimately can think about what this is going to look like. So I don't remember if it was this section or another that asked me why I was drawing out the curves the way I was last class. Well, the reason why is because if I have this continuous random variable x, a normal distribution will always kind of be shaped like a bell curve. Right? We'll talk about how this shape changes here in a little bit, but the idea of this normal distribution is it's centered around whatever the mean of this random variable x is. Right? And we remember kind of what's on our y-axis. It's really kind of showing us like the probability. So values that are very far from the mean have low probabilities of occurring, but values that are really close to the mean have higher likelihoods of occurring. That's really what the normal distribution is telling us. The uniform said everything's equally as likely. The normal is saying values near the mean are more likely, values further from the mean are less likely. This is kind of our normal distribution, kind of has this nice bell-shaped curve to it. Now, how do I know what this continuous line looks like? There is some function that I could use to then have x and y pairs and like plot out or graph this line. Right? That's what we would kind of call our probability density function. So that was a little bit easier for the uniform distribution. If we look at that probability density function for the normal distribution, and when I forgot to mention this, I'll mention this in a second. It's going to look something like this. Now, don't write this down. We're not going to be kind of using this function, but it'll be floating around behind the scenes. Okay. So this is a pretty nasty function to have to deal with. Now, we'll notice like really what are the components? Like you're looking at different values for x, and you're trying to come up with a probability measure that you could also plot. So we've got the mean, we've got the variance in there. We end up having both those natural numbers, e and pi, which is kind of, I guess like shows up in nature and biology and all this stuff all the time. And it happens to have these two natural numbers that they kind of, pi never stops. It's a very unique number. It's kind of, I don't know, maybe somewhat like poetic, or I guess if you believe in a God or something like this is maybe proof, right? Because it's very bizarre, right? So how can we use this probability density function to do things like, well, what's the probability if I'm looking at a variable that's normally distributed? What's the probability that it's in between two values? Well, I could integrate that function that I just showed you from A to B and actually come up with the area underneath that curve. Now, that's going to not be fun, and we're not going to end up having to do that. We've got a way to get around that. But ultimately, you could use that function to do something like this. Okay. Now, instead of integrating that function from whatever values, plugging in your mean and your variance every single time, there's a much easier process that will eventually kind of have worked through by the time we get to the end of today's class. Okay. But this is kind of what's floating around in the background. Okay. So what are some characteristics? We've seen the function, but what are some characteristics of this normal distribution? Well, I kind of already mentioned it's centered around its mean, but also it ends up being symmetric. So if I were to fold it in half around that mean, let me see if I thought I would have had a line there, maybe not. So if I fold it in half around this mean, it would exactly kind of fold on top of itself, right? It's symmetric, okay? The mean will be equal to the median. So it's a nice property we can kind of think about. And then also it's going to be defined by its mean and variance, right? Part of that probability density function, we had the mean and the variance in there. So how is that going to change the shape of my normal distribution? Okay. So here, if I think about, let's say I've got some random variable X and I've got two different groups. Right? So maybe group one, it's normally distributed around this mean. But our second group, we know, has a higher mean. Well, let's assume the same variance. What that's going to do is just, well, it's still normally distributed. It's just that it's centered around a higher mean. Right? So differences in means just shift that normal distribution along the x-axis. I don't think that's too bad. Let's think about the other thing that defines it, which is its variance. So maybe I start out. Here's my normal distribution for group one, centered around their mean. And I don't know, maybe the variance is something like 10. Okay. I then think, okay, group two has the same mean. So it's going to be normally distributed around the same value, but the variance is higher. Right? So if the variance is higher, how's that going to change my distribution? Like I shouldn't be drawing the exact same thing because it's got a higher variance. Well, a higher variance is going to tell me that values further from the mean are going to be more likely, right? Remember, my y-axis is kind of representing probabilities here. So values further from the mean are going to be more likely, but values really close to the mean are going to be less likely if my variance is higher, right? Higher variance just tells me that the data is more spread out. And so having a higher variance essentially flattens our distribution or makes it shorter, if you want to think about it that way, right? Difference in means shifts on the x-axis. Differences in variance or higher variances will kind of flatten or shorten, right? Or change where we're at on the y-axis. So you can have all these different normal distributions. They'll have different heights. They'll be at different locations on the x-axis, but we can, they're still normally distributed. Okay. Any questions over anything there? Okay. So, we've got all these normal distributions. I've kind of already talked about, right? Difference in mean shifts it, higher variance flattens those distributions. These are just additional kind of slides, additional ways of looking at that. If I'm looking at something like this, which group here would I say has a higher mean? This is human height. Yeah, if we think about this male distribution, it's centered around a much higher value than the female height distribution. Which one of these groups has more variation in their height? Yeah, right. So we said a higher variance would flatten that or shorten that distribution. So the shorter distribution here, I guess no pun intended, is kind of the male distribution, which means that it has a higher variance, right? It's a flatter distribution. It's more spread out because it has this higher variance. Okay? So we can look at the distributions and kind of determine these things. Okay? Now, a lot of what we're going to do moving forward, like we'll make statements about means and averages. But now that we're thinking about these distributions, any two individuals, right? I could end up with a male that has a height from this part of the distribution and a female that has height from this part. And so then that, female height would be greater than male. But we usually talk about things on average, right? The mean of this distribution is greater than the mean of this other group's distribution. And it may not be like male, female height. This is, could be like, maybe we're looking at temperatures across countries or across states, or we're looking at something else that's normally distributed across companies, although there's not probably as many examples there. But any questions to this point? Also, I'm losing my contact. Okay. So if we remember, last class we had a uniform distribution. The curve was like this flat line, but we said that the area under that flat line, under that curve was 1. Same thing's going to apply for a normal distribution. If I was to integrate that probability mass function from negative infinity to positive infinity, I should end up with an area under that curve of 1. Okay. Now, for now, take me at my word, but I'll show you why this is the case by the time we end class today. So if I were to go 1 standard deviation below, remember sigma represents our standard deviation, mu here represents our mean. If I go 1 standard deviation below and above that mean, the probability I see this random variable X take on a value in between one standard deviation above and below is always going to be about 68%, or a probability of 0.68. Okay. Like I said, for now, just believe me. Well, I'll end up proving this to you by the end of class. Well, what if I said, what's the probability I'm in between two standard deviations above and below? That probability should be higher, right? I'm just creating a wider range of possible values. I'm going 2 standard deviations above and below that mean. So the probability I'm at 2 standard deviations above or below that mean is always going to be about 0.95. And if I go 3 standard deviations, I'm up to 0.997, right? So I'm just creating a wider range of values, so that probability is going to increase. Well, you know, what use is this? I think hopefully by the end of the class, this will make a little sense of why I'm showing you this now. But also, I don't know if any of you in some of your other courses or what degrees, what sequencing you take, but maybe you've heard 6 sigma, that term kind of thrown out there. So the idea is here at 3 sigma, 3 standard deviations, I'm already at 99.7% chance that I see a value somewhere within 3 standard deviations of the mean. If I go to 6 sigma, 6 standard deviations above and below, I'm so close to 100%. It's, you know, I'm out to some crazy decimal. It's like 0.9999999, right? So that's this is kind of where 6 sigma is coming from. Once we go through some more topics, I'll probably bring this up again because we can actually really think about what 6 sigma is trying to do. But it's kind of related to already what we're talking about here being 6 standard deviations above or below. Okay. So how am I coming up with these values, right? Well, we'll have to go back a little bit here. But we can think about, we start out with a normally distributed variable. Now, that normally distributed variable is going to have its own mean and variance, and right, that's what defines it. So, you know, last class, I guess here, I'll just do this. So last class we talked about, you know, maybe we have random variable X, it's uniformly distributed, and here's its min and here's its max, right? Those were the 2 things that defined a uniformly distributed variable. Today we're going to say we've got a normally distributed variable, and you know, maybe it's, I don't know, 10 and 50, right, as our mean and our variance. Right? This is just kind of how we write this out in notation. So I've got a uniformly distributed variable, here's its min and max. I've got a normally distributed variable, here's its mean and its variance. Okay. So we're starting out with a normally distributed variable, but what we're going to end up wanting to do is convert that into what we call a standard normal distribution, which is a normal distribution that has a mean of 0 and a variance of 1. So the reason why we like this, first of all, if I have a variance of 1, what's my standard deviation? Square root of the variance. So the square root of 1 is just 1. So I've got the variance and the standard deviation are both 1. If the mean is centered around 0, then I get this really nice interpretation, which is if I'm looking at different values for X, that just tells me how many standard deviations away from the mean I am. Think about if I saw it at a value from a standard normal distribution and it was 1.4. Well, the mean is 0. So that value of 1.4 is 1.4 away from the mean. If my standard deviation is 1, being 1.4 away from that mean of 0 is being 1.4 standard deviations away. Or think about if that was an X value of 2. Well, I'm 2 standard deviations away if the standard deviation is 1. So it has this really nice interpretation, all the different values for X, if it is standard normally distributed. Okay. You can also imagine back in that probability density function, if I plug a 0 and a 1 in, a lot of things become a little bit more simple. It's easier to integrate that function. And also people have already kind of done the work for us. Right? But this standard normal distribution is nice because once we have a standard normal distribution, we can think about these different values. And instead of X values, if it is a variable that's standard normally distributed, we typically call them Z values instead. So these different Z values, right? -2, well, that's just 2 standard deviations below the mean of 0. A Z value of 1, well, that's 1 standard deviation above the mean of 0. So it has this really nice interpretation, which is it's the number of standard deviations away that value is from the mean. Right? Now the mean happens to be 0 here, but that's why it kind of has this nice interpretation. So how do we start out with a normally distributed variable and get to this point of a standard normal distribution, right? So I might start out with a normally distributed variable and it has, I don't know, mean 10, variance of 50. How can I convert that into what we would have a standard normal distribution where the mean is 0 and the variance is 1? Okay? Because if we can do that, if we can convert that original variable into a z value or a z variable, then those values for z will have really nice interpretations, which is just the number of standard deviations away we are from the mean. So the way that we'll do that is using this formula. Okay? So we'll take this original variable x, we'll subtract the mean, and we'll divide by the standard deviation. So if we do that, our new values, which will be called z values or z scores, should be standard normally distributed. Okay? Now you'll have to kind of take me at my word here for now, but I'm about to show it to you in a second. I just want to make sure everyone kind of can write that equation down if they wanted to. So let's say I start out with a nice kind of normally, actually, I don't want to do this. This should be 6 and 8. Sorry. Small data set to kind of think about this, but it is symmetric. So we'll think about this. It could be a normal distribution or a normally distributed variable x. Okay? So the first things we need to know, what defines this normal distribution? Well, what's the mean and what's the variance of x? Right? So to get the mean, it's just old stuff. We add these numbers up, divide by the number of numbers we have. So if I add these up, divide by 4, I get that it has a mean of 5. Okay. You know, I could then go through, find the deviations from that mean squared, add these all up, and then I'm looking at a population variance here. So I would divide by the number of observations I have. Right? So first I'll go through, take this value, subtract that mean of 5. So 2 minus 5 is negative 3 squared is 9. 4 minus 5 is negative 1 squared is 1. 6 minus 5, 1 squared is 1. 8 minus 5 is 3 squared is 9. I then add up all those deviations squared and I end up with this nice kind of thing where I've got the variance and the mean are the same. That doesn't have to be the case, but it just happened to be with this small data set that I did. Which would mean the standard deviation is just what? Square root of 5. Okay. So this is my original variable x. I've calculated its mean and its variance, and it's normally distributed. I want to turn it into some z values. Okay. So maybe we can think about separating this here. So to create a z value, I'm going to subtract the mean and divide by the standard deviation. So that was our equation that we had. Okay. Subtract the mean, this is a terrible signal, and divide by the standard deviation. Okay. So 2 minus the mean of 5 would be negative 3 divided by that standard deviation of which was the square root of 5. Then the next x value, 4 minus the mean, so negative 1 divided by that standard deviation, which was the square root of 5. 6 minus the mean is 1 divided by that standard deviation. 8 minus that mean of 5 is 3 divided by the standard deviation. Okay. Any questions there? Yeah, so anytime we see a z-score, because it's interpreted as the number of standard deviations away, notice that any values for x that are below the mean, well, they'll have negative z-scores. There are a certain number of standard deviations below the mean. Any values that were above the mean have z-scores that are positive, because there are a certain number of standard deviations above the mean. Any other questions there? It's a good one. Hold on. We'll get there eventually, I promise. Okay. So we've got these z values. I'm just trying to prove to you this idea that they will be standard normally distributed. And then we'll go back to thinking about how we can use them. So I've got the mean. I just add these values up and divide by the number of numbers I have. So I've got 4. So what if I add these up, notice, add to 0, right? Everything, if I have a symmetric distribution, everything will equally kind of cancel out. So by subtracting the mean, I've demeaned, or sometimes what's called standardized the data so that the new mean is 0. Dividing by the standard deviation, if we go through and find the deviations from this mean of 0 squared, well, negative 3 over the square root of 5 minus 0 is just negative 3 over the square root of 5. Square that, I get 9/5. -1 over the square root of 5 minus 0 is just -1 over the square root of 5. Square that, I get 1 over 5. Kind of go through this process. So now to calculate my variance, I would just add up all these deviations squared, divide by the number of observations I have, which is 4. So if I add all these up, I end up with what? 20 over 5, which is 4 divided by 4. I end up with a variance of 1. So this is just kind of a quick toy data set example where you can see if I have a normally distributed variable, if I subtract the mean, divide by the standard deviation, and calculate these z-scores will always have a mean of 0 and a variance of 1. Okay. So hopefully that justifies it to you, which the next step is then, okay, we can calculate these z-scores. We know that they're standard normally distributed, but now what, right? So things we've already talked about, this idea that positive z-scores, we're going to be a certain number of standard deviations above the mean, negative, a certain number of standard deviations below. But also that the z-score for the mean is always going to be 0, right? If you think about why, if the x value I'm looking at is the mean minus the mean is always going to be 0, right? So the mean is always going to have this z-score of 0, but then we can map out, then we can map out different x values to different z-scores. So I've got something in the slides for this, but I think I want to draw this out instead. So let's say I've got this continuous random variable that's normally distributed, x, right? It's centered around its mean. And then let's think about different values. So let's say maybe we want to look at something that is 1.3 standard deviations above the mean. Right? And we want to map these out onto what their corresponding z values would be. Okay? Well, if my z-score equation is this, notice that for the mean, I'm always going to end up with a z-score of 0. Because the mean is 0 standard deviations away from the mean. So the z-score should be 0. That's the interpretation of our z-scores. Now, I don't have to do the math, but what should the z-score for something that is 1.3 standard deviations above the mean be? I literally just said the definition of the z value, right? So it's the number of standard deviations away from the mean. So if I'm 1.3 standard deviations above the mean, the z value would be 1.3. And if I'm looking at something that's 2 standard deviations below the mean, that maps out to a z-score of -2. Right? So things above the mean, positive z values, things below the mean, negative z values. So I think the one I have in the slides, I actually show you. I stole this from the book because I actually did like this part of it. You've got different number of standard deviations above and below, and they're kind of corresponding z values. So you could just, fill in as many of these as you want, but 3 standard deviations below the mean, z value of -3. 1 standard deviation above the mean, z value of +1. Okay? So now that we have these z-scores, why the hell are we doing this, right? And so the original question might be something like, I want to find the probability I'm in between 2 values. This original variable x, maybe it's human height, is in between 2 values. Okay? Well, I don't want to do the integration, right? And, the probability density function was complicated. This cumulative density function is even messier, right? However, people have already done this integration for us. I think that's what I've already said, right? And we've got the standard normal table, or that z table, okay? So if we can convert our original variable x and the values we're interested in, a and b, we can convert those into z values, but we can then look these z values up in the table and find the cumulative probability associated with them. Right? So let's say as kind of our motivating example, we want to find the probability that the z value we found, which was -1.29, what's the probability we saw that z value or anything below it? Okay? So what's the probability I saw this z value or anything below? And maybe this corresponds, this z value came from an original x variable, like maybe it was human height, so maybe it was 64 inches. We converted that into a z value, it was -1.29. So what's the probability someone is 64 inches or shorter? Or what's the probability that their height is 1.29 standard deviations below the mean or even further? We're saying the same thing then, right? So So the probability that you're below the original X variable is the same as the probability that you're below whatever Z value that would correspond to. Okay? And now that we have a Z value, we can just use this integration that people have already done and use that table. Okay? So what's this table look like? It's really small here. So I'm going to open up the PDF. And if we look here, the first page of this table, it's kind of telling us, okay, these numbers in the middle here, these are probabilities. These are cumulative probabilities. The probability that you see that Z value or anything below it. So all those numbers in the middle, represent probabilities. And the row and column headings are your different Z scores. So, negative 3.62, right? I use the row heading to look up the first decimal. So negative 3.62 would be negative 3.6. And I use the column headings to look up the second decimal, 0.02, right? So negative 3.62. The area to the left of that Z-score, or the probability of seeing that Z-score or anything below it, 0.0001. Well, we were interested in that Z-score of negative 1.29. So I've got this zoomed in, which is why it's always kind of better to have it in front of you, because like the column headings are going to disappear when I scroll down here to find negative 1.2. But we'll remember that we want to look up negative 1.29, so our second decimal will be this 0.09. So negative 1.2. And then go all the way over to the last column, which was represented that decimal of 0.09, or our second decimal. So the probability I see negative 1.29 or anything below it would be 0.0985. So I can look up different Z values and find the probability that I saw that Z value or anything below it. Okay. Any questions on that? Before I keep moving here. So I've got some nice labels kind of here on the slides, right? So you've got your second decimal is the column heading. The first decimal of your Z value is the row heading. Where those two things meet, this represents the probability you saw that Z score or anything below it. And just to kind of, I guess, bring some of these points together. So, really what I'm thinking about there is I've got some original variable X. And like I said, maybe this is human height. I don't know. It's not the most interesting example. But maybe I'm interested in finding the probability of what's the probability that I see someone be 64 inches or shorter? Well, this is a normally distributed variable. The integration is kind of nasty. But because I know that people have already put this table together for the standard normal distribution, I can map this value out to a Z value of negative 1.29. When I looked at that Z value of negative 1.29 up in the table, it told me the probability I saw that Z value or anything less than that was 0.0985. So really that also corresponds to the probability I see someone be 64 inches or shorter, which corresponds to be 1.29 standard deviations below the mean height or anything further below it, would be the exact same thing. Okay. So this is the kind of the usefulness of these Z tables, right? I can start out with any normally distributed variable. I don't have to worry about the integration. Just do a simple conversion into a Z value and find these probabilities from that table where people have already done that integration or calculate these cumulative probabilities for us. Okay. Any questions up to this point or kind of, I don't know, any confusions? Yeah. So if I asked you instead, what's the probability of being above 64? What could I do? Yeah, so there's not you can't look it up directly on the table, but anytime you want the area to the right, you can look up the area to the left and just subtract it from 1. Yep. Any other questions? Okay. So I want to point something out here before we kind of go back to off the dot cam. So my Z values will always be centered around 0. So what's going to be the probability that I see something above or below the mean? Both of those probabilities should be what? If it's symmetric, 0.5 and 0.5, half on either side. Right? Area under the curve being 1. So remember, if I have the mean of 0, what if I'm looking up a negative Z value? The area to the left of this negative Z value will always be what? less than 0.5. If the area to the left of the mean of 0 is 0.5, then the area to the left of any negative value has to be something less than 0.5. If I'm looking at any positive z-value, the area to the left of a positive z-value always has to be greater than 0.5. So we're actually going to end up with, let me see here. So here is our first page. Notice for all these negative z-values, the probability of seeing those negative z-values or anything to the left or anything below them, all these probabilities are less than 0.5. Oops. Until I get to 0, 0.00, and then the probability is exactly 0.5. And then if I want to look up positive z-values, which is the second page or the back side of this z-table, all of those probabilities, the area to the left of a positive z-value, these will all be greater than 0.5. Okay? That's just something I kind of wanted to point out at this point. Okay? So notice, if I look up negative 1.29, I found the probability of being to the left of that is 0.0985. But notice, what if I look up positive 1.29? I get 0.9015. Okay? There's something kind of interesting about that. So, if I looked up negative 1.29, I found that this area was 0.0985. When I looked up positive 1.29, I actually didn't need to use the table. I could have actually figured out what's the probability I see something below positive 1.29. Well, think about it. If this is a symmetric distribution, the area to the left of negative 1.29 would be the exact same thing as the area to the right of positive 1.29. So if I know the area to the right of positive 1.29 is 0.0985, right? So this area, 0.0985. How can I find the area to the left of positive 1.29? Yep. So we get what? 0.9015 here, which when we look that up on the table is exactly what we would find. Right? So sometimes we can like use this idea of being symmetric to not have to use the table as many times, right? I mean, I could look up, it's pretty easy to look up 1.29 here on the table and just get that probability, but I could have also done that just knowing the area to the left of negative 1.29, right? And the idea that it's symmetric, and then use the complement rule. So there, you know, we kind of start throwing together a lot of things that we've done in the past, multiple ways of doing the same thing sometimes. Okay. Any other questions there? I probably should have used a red marker. I guess that now I'm looking at the green and the blue kind of look similar. Okay. We're okay with this for now. Kind of work through some more examples here. So, all right. So we got this. We've already talked about kind of finding the probability of being less than positive 1.29. I've got some kind of z-scores that we'll see pop up a lot because they correspond to some really good benchmark probabilities. But I want to do one more thing here and try to prove to you what I said earlier. Okay. So let's say I've got this normally distributed variable x, got some mean, and I want to think about what's the probability that I see something in between in between one standard deviation above and below that mean, right? What's that probability? Okay. So I can map that out to z-scores. Right? So try to draw this. The mean should have a z-value of what? 0. I can go through the math, right? I could say, okay, here's my z-score equation. So my x value is being one standard deviation below the mean. Subtract the mean, divide by the standard deviation here. This cancels, so I've just got -1. Or if I remember the definition of my z-score, if I'm looking at an X value that's 1 standard deviation below the mean, that's going to correspond to a z-score of -1. And being 1 standard deviation above the mean should be a z-score of +1. Right? Probably need to write the positive sign there, but. So now that I have this, right, I can look up that z value of -1 in the table. It'll give me the area to the left of -1. If I have the area to the left of -1, that's going to be the exact same as the area to the right of +1. Once I have those two areas, to get what I originally wanted, which was what's the probability I'm in between, right, or within 1 standard deviation above and below the mean, right, I could take the area that I found here in these tails and subtract it from the entire area of 1. So I'm going to look up the z value of -1. And this is something else to kind of point out when using this table that's a little bit weird. If I don't have a second decimal, like notice like 0.30 is what I would look up. So here I wanted -1, so -1.0, and then this first column is the second decimal of 0 as well. So -1.00. The probability I see that z value of -1 or anything below that, 0.1587. Okay. So I've got this area here. The table told me was 0.1587. Okay. So if I know the probability I see -1 or lower is 0.1587, the probability I see a z value of +1 or anything higher, symmetric distribution. So I know that this would be 0.1587 as well. From there, to find that area that I originally wanted, the probability of being in between 1 standard deviation above and below, I would just subtract those both from 1. This is what, 0.3174. So 0.3174. This works out. If I round this to the second decimal, I'm getting approximately 0.68, which is that original value I showed you earlier, right? Maybe that was only the 3 decimals. Here I've got it to 4. I don't know, just didn't want to use the mental math there. So we're around 0.68. So that's where that number is coming from, right? You could do the exact same thing. Go 2 standard deviations above and below. You'd have a z value of -2 and +2. Work through the same process, and you would find that value of 0.9544. You could do 3 standard deviations above and below, work out the same process, look up, the z values of -3 and +3, and you'd find the exact same thing that I showed you earlier, which is like 0.997, something like that. Right? So that's where those values are coming from, right? We could actually find the probability of being any number. We could find the probability that I'm 0.3 standard deviations above or below, kind of using this same process. Okay. Now we'll start. I know there's a lot we kind of had to build today, so this is not the most fun lecture, especially because, like, I mean, I can give you some toy examples and mention variables here, but we can't actually work through an entire problem yet. So on Friday, we'll have everything we need now to really work through some entire problems and kind of have some better motivating examples. But kind of getting used to looking up these z values, that's one of the questions on that online quiz that you have to have done before we start class Friday. But just kind of get that printed out or start to get used to using that. We're going to be using that table a lot moving forward. Okay. So looking up different z values, knowing that the table tells you the probability of seeing that z value or anything below it, or the area kind of under the curve and to the left, that's what you want to kind of keep in mind there. All right. The table always gives you the area to the left of whatever z value you look up. Okay. Any questions on anything here? I want to go back to the slides and do a little bit more before we end today. Okay. So let me see here. We'll kind of touch on this. I've already mentioned some of this stuff too, so some of this will really breeze through on starting on Friday. I already talked about the probability of being to the left or the right of the mean. I had some things down here at the end. I just thought this was kind of interesting. So here's an example. If I took human height, I had a data set that's from the CDC and it had human height. I think I might have done just male height here because we have the bimodal issue if we put males and females in the same graph. But kind of notice male height is like really close to a nice normal distribution, right? So I said this pops up in biology and nature a lot. It also like shows up everywhere in like human performance. So I don't prescribe to the ideas of CrossFit, but I saw this pop up somewhere and they were like boasting, they have like their workouts or whatever, and they recorded all this data. And so I'm sure they like just wanted to show how many reps people could do or whatever. But I just saw this and I was like geeking out about how insanely close to a normal distribution this human performance data is, right? Especially like the female distribution. I mean, that is almost, I can't draw a normal distribution that looks that good. And that was the actual data, right? So we see this pop up all the time. I've got some other examples. We'll talk through some stuff, but like I had some powerlifting data set and I like did some stuff with it really close. I mean, these are a little bit skewed, right? A lot of times we look at this human performance or these different biology like statistics, they almost always follow this nice normal distribution. And so we definitely want to know how we can deal with those. Okay. All right. So make sure you get that quiz done before Friday. I will bring the exams to hand back with me at the beginning of class. And other than that, be safe and I'll see you on Friday.